the official closing of ICFP itself. So the first of two talks is by Dominic Orchard, and he's going to be talking about combining effects and co-effects via grading.
Great, thank you very much, Jeremy, and thank you to my co-authors, Marco Gabwardi, Shinya Katsumata, Flavien Bouvard, and Tamo Ustalu. Now, the context of this work is about studying common patterns in the underlying structure of computation, so that in the future we can build languages where we can do more fine-grained reasoning about programs. Now, specifically, I'm going to be looking at effects and co-effects in this work. So I'm sure you're all very familiar with effects. I'm going to describe those as aspects of a computation which change the execution context. For example, mutating a variable or throwing an exception and changing the control flow. Now, co-effects, I appreciate they're less well known. And we describe those as aspects of a computation relating to how a program uses or depends on its context. So the main way that programs depend on their context is via their variables. And there are various properties of variables that we can track using a coeffect paradigm. So for example, whether a variable is used or not, whether it's live or dead, and I mean a variable in the mathematical functional programming sense. Information flow properties, like whether a variable is high security or low security. Notions of linear logic, whether a variable can be used once or at most once, or bounded linear logic, where we can put a bound on how many times it's used, which is used a lot in resource analysis. Understanding which deconstructors are applied to variables to do strictness analysis, and various other things. Now, the coeffect paradigm also includes analysis of and understanding how programs depend on the wider context, so things like hardware resources, library versions, and even Haskell type class constraints. But I'm not going to be talking about those in this work. It's more to do with per-variable coeffects. Now, in the literature, there's two kinds of paradigms for understanding coeffects. One is via a type-directed static analysis, via a type and coeffect system. And there's a few flavors of these in the literature. One that's a whole context analysis, which annotates a typing judgment with some information about how the program uses the context. And one's the per variable that track for each variable what are the demands that the program makes on those variables. In another line of work, is to define a coeffect meta-language, which is a typed calculus where there's an explicit type constructor, which is annotated with some effect information for describing how a program depends on its context. And this was shown by Brunel et al. In 2014, and it corresponds to a generalization of the linear exponential constructor. And we're going to be following this paradigm of the coeffect meta-language, and some of the other aspects of the related work. So all of these kind of systems have a semi-ring structure on this coeffect information, which I'll explain, and they also are based on a graded comonadic semantics, which I'll also explain. So in this paper, we're studying the interaction of effects and coeffects. And there's two examples in the paper that we do in some depth. One is where we have security levels related, so that's the coeffect, where we're tracking whether what level of security our variables are, and then their interaction with non-determinism effects. So if a high security computation does some non-determinism, and I'm a low security observer, I can't see everything that happened with that non-determinism, I just know that some effects happened. So it's a kind of masking. The other is the interaction between exceptions and linear reuse bounds. So if an exception is thrown, then future parts of my computation have their resource information changed because the exception so interrupts the rest of the execution flow. So we have a small calculus, typed calculus, which is based on the linear lambda calculus with primitives for effect and coeffect composition. We're not saying this is a programming language you should use, but it's more of a tool for describing the semantics of languages which have effects and coeffects and their interaction. And we're going to have two special type constructors in this language. One T, which is indexed by some effect information E in red. And so this is the type of an effectful computation that does some effects E, described by some algebraic structure. And this box modality type constructor, which describes the coeffect requirements on variables. So this says that I have a program T, which depends on its variable X in an R-like way. Now in the paper we use some slightly different notation. I'm using some simplification for the talk, but I've used box to stir up your modal desires because there's a modal logic underneath this. And we've got this coeffect and effect algebra underneath, I'll explain. And the semantics is graded, and it uses monads, graded comonads, and graded distributive laws. So in the talk, I'll just outline these 3 points. So imagine we have the following situation. We have two functions, one of type a to tb, the other b to tc. Now these don't compose by normal function composition, but if t has the structure of a monad, then the monad operations give us this composition to get a function of type a to tc. And the monad laws say that this composition is associative and that it also has an identity where we can lift an a into a ta. And it was shown that this was, we've discovered and we've seen, and Moji showed us that this is really useful for modeling effects because we can use T to model the changes that a program does to our environment, things with state and so on, and the structure of a monad nicely captures the sequential composition, which is common to lots of notions of effect. Now imagine this other situation where the type constructor has some extra information which refines what's going on inside. It tells us a bit more about what the effect is. And this information is going to have a monoid structure. Now what a graded monad provides us is the same kind of composition, but now we can see that if we've got a computation that does effects E, one that does F, then when we do their composition, the monoid of the monoid dot operation is used to describe that E dot F effects are being carried out. And the identity is annotated with the unit of the monoid, so it shows us that the unit is really constructing a computation that is trivially pure. So this is very powerful. We can then have a semantics which is refined by more information about the effects, and we can understand really what's going on underneath more clearly. Now the dual notion to this is graded comonads, and so if we have a computation which is from, well, it's a function from A to B, but it also has some requirements R, and we've got another function which has some requirements S, and we have some monoidal structure to those blue indices, then a graded comonad provides this composition where we do R times S for the requirement, and we also have an identity operation for this composition which says we're just doing a trivial dependence using one of the monoid. So this is a very, very brief introduction to graded monads and graded comonads, but the general paradigm or slogan of graded semantics is that we want to match the structure of computation with structure in the indices. So we're doing some composition here, and so our indices have a monoidal structure which tracks the composition at the type level, at these index level. So our core calculus is basically built to give us access to the underlying operations for modeling effects and coeffects in this graded way. So it's in 4 parts. We've got a meta-language for effects, a comonadic meta-language for coeffects. The rest is linear lambda calculus, and that's controlled by Coeffects as well. And then something called a graded distributive law, which we're going to use for the interaction of the effects and coeffects. So the first part is this effectful meta-language component, which is parameterized by some pre-ordered monoid of effect information. And then we have this let binding construct. If you use Haskell, it's a bit like the do notation, which says if we've got some program T1 which has effects E, we combine that in the scope of T2, which has a free variable X of type A, and it does some effects F. So when we compose those, we have in our type that E compose F effects are being performed. So this is really just exposing the graded monad structure underneath, and we can lift any value into the trivially effectful computation. So as a simple example that we use in the paper, and I'll use in this talk, is effects that are exceptions with a very simple analysis at the type level that says we can find out whether something is definitely throwing an exception, bottom, or if it may succeed. And so the monoidal structure uses meet for the binary operation, so if we're composing 2 computations and one of them definitely throws an exception, then the composition definitely throws an exception. So the next part is for coeffects, and that is parameterized by a semi-ring. And to make things nice and concrete, I'm going to take the natural numbers semi-ring that we all know, and this models Girard's notion of bounded linear logic, where we count in our types how many times we use a variable. So if we've got some program T with a free variable X, this rule called dereliction annotates X with the type constructor box1, which tells us that we've used the variable once. The promotion rule says, I've got this expression T of type B, and let's say I want R copies of T. Then we also need to multiply all our requirements in the context by R. So this notation box gamma means that everything in the context has the coeffect box on it with some information, and then on the bottom we're lifting r multiply to multiply each part of the context by r. So for example, if I've got this expression x plus y, its coeffect type says that x is used once and y is used twice, and let's say I want 2 copies of that output, then we multiply the context by 2, and we now know that x we need 2 copies of and y we need 4 copies of. Now when we have this box on the right, you can think of that as a coeffect capability. We're providing the capability here for 2 copies of an integer. So this let rule provides a way to compose capabilities with requirements. So if T1 provides r copies of A, we can compose that along X to provide those copies to T2. And that's the basic structure that uses the monoidal part of the coeffect. The rest, one part of the monoid of the semi-ring. The rest is used in the linear lambda calculus part. So we have the axiom rule, the abstraction rule, and app rule. And this is linear lambda calculus without any products or coproducts. It's just with implication. And you'll notice that there's this plus in the app rule between the 2 contexts, gamma and delta. Actually, plus was on the other slide, so you may have seen that and been confused. And this is actually used to control contraction, and it's defined in terms of the coeffect plus. And basically what plus does is union 2 contexts together, but if x appears in both contexts, then it's ill-formed. So this is the usual control of contraction that we have in the linear lambda calculus, unless both x's are of coeffect type, and then we add together their indices. So if we've got box R and box S for x in both contexts, then we can contract using the plus of the semi-ring. Now related to this, we can use the coeffect 0 for weakening. So this sub-rule provides us access to approximating effects and coeffects, which I won't talk about, but it also provides us a way to weaken with some arbitrary other context, delta, as long as we put the 0 annotation on every variable. So for BLL, it shows us, bounded linear logic shows us that we've weakened, but we're not using those variables yet. So that's almost all of the core calculus, and I'll show the next part via an example. So we've got bounded linear logic coeffects, we've got this simple exception effect system, and let's say we've got this program T1, which we know is definitely providing an exception. And inside it's of type A, and we want to compose this with a program T2 along this free variable x, which is saying I need r copies of something of type A. Now on the right-hand side, we can do a bit of manipulation. I won't show you all the syntax because it's a bit technical, but we can basically lift it up to take a effectful computation that's with an exception, and we know with exceptions that this just gets passed through. Exceptions subvert the control flow, so we definitely throw an exception at the end. So this means that T2 actually never gets run. Now we can try and compose this on the right. We can derelict everything in the context, just put it with the 1 coeffect, make sure that everything's coeffectful, and then we can promote to say, right, I'm going to have r copies of my exception. But do I really need r copies of my exception? Because I'm not going to read r copies of A here because those A's aren't going to exist. So I only need 1 copy of the exception, which I can just pass through to the end, and I'm not even going to run 2. So our goal is to have an effect and coeffect interaction that says that exceptions cancel out resource requirements. So that means on the left here, we want to set r to be equal to 1. But we're not done yet, because these 2 things don't have the same type. We've got box on the outside and box on the inside on the right-hand side. Now, if we squint a little and don't look at the indices, this might remind us of the notion of a distributive law. And in category theory, there's a well-defined notion of a distributive law between a comonad and a monad. Or maybe you're a Haskell programmer and you've seen things like the sequence operation, which is a distribution between the list monad and any arbitrary monad, which is a bit different to a comonad, but I'll come back to that. But this isn't going to work because it doesn't have indices in it. So we could imagine trying to have an index distributive law. But this still isn't enough because r over here is equal to 1. We've got 1 and r, so this isn't going to provide us any effect and coeffect interaction. It doesn't describe this interaction for us. Now let's remember our graded slogan. We want algebraic structure on the indices that matches the algebraic structure of the computation of its semantics. So if we've got a distributive law in our computation, in our semantics, well, we should have a distributive law between the monoids that describe effect composition and co-effect composition. Fortunately, this already exists in maths. It's used a lot in quantum group theory. And there's a notion of a Zappichet product, which is a way of putting two monoids together. It's a way of forming a product of monoids. And it corresponds to a distributive law of RE over ER. And it can be decomposed into something called a matched pair, which is basically a way of calculating, given an R and an E, calculate me a new R, given an R and an E, calculate me a new E. And it has various laws, which I'm not going to go through, which basically say that this preserves the notion of composition on both sides. And this is exactly what we need then to provide a notion of composition for things that are effectful and co-effectful and that interact in their monoids. So we get this graded distributive law, which is parameterized by one of these matched pairs. And so we use iota on the left, which says, okay, I've got coeffect R and effect E, and I want to combine them to calculate some new coeffect due to their interaction. And kappa on the right calculates the new effect due to their interaction. So this is the sort of general law. And that's a primitive in our calculus. That's the last part, really. So we've got this. We want to cancel out our resource requirements with an exception. So we're going to define a matched pair for our distributive law. Well, we're not having, the effects are not going to be changed by resource requirements. So we set this to projection. So that specializes our law down to something a bit more simple. So here we've really got effects changing coeffects rather than coeffects changing effects. But very importantly, we want to say that if we've got an exception and requirements are, then those requirements go away because of the exception, and we set the coeffect to 1. And this is exactly the piece we need up here, which says if we've got one copy of an exception, we can turn this into an exception with arbitrary copies of stuff which we actually don't even have anyway because it's an exception. And those are the types we needed over here. And so we can compose those together, let binding. And now we see, yes, we've got the exception coming out at the end, and we only need one copy. We only needed one copy of all of the things gamma to compute our exception. And so that solves the problem. And to be complete, we should also fill in the other case for iota, which says, well, if we don't know whether we've got an exception or not, we better preserve all the resource requirements, which gives us this other more simple distributive law. So until we added that distributive law, we had coeffects and effects in the calculus, but they were separate and never interacting. And via this structure, we can now let them interact and start describing some interesting situations. And in fact, we don't just have one distributive law in our calculus, we map out a design space. Because already we've done box T over T box, but you could imagine trying to go the other way around. And there's various bits of maths where this is used, so we thought, okay, we should at least think about the possibility of having this. There's also a choice about which direction the data flow is going. So I could have my effect TE on the right, and I could compute a new, on the left, and I could be computing the new effect on the right. Or I could do it the other way around. So in my example, I had it this way around, but you could also consider a backwards data flow property, and the same for coeffects. And so there's another dimension of choice there as well. So overall, this leads to a family of distributive laws, 8 different distributive laws that correspond to which way around you're commuting things and which way around the data flow goes. And in the paper, we show 2 examples in this space. We wanted to sort of set the scene for future work and give a design space of what could be done. So really, the distributive law in our language looks like this. It's parameterized by a format, which is one of these things, which tells you which way around everything is going. So I've touched on the semantics. We've got a graded strong monad in there, which is due to Katsumoto. We've got a graded monoidal comonad, which appears in lots of coeffect work. But the new thing is this family of matched pair graded distributive laws. And of course, we prove this sound. So we set up a foundation for thinking about effect and coeffect interaction. And we think there's probably lots of really exciting possibilities that we've started playing with, but we haven't done all the proofs yet. So we can imagine having exceptions which maybe are high security and contain some high security information, but if I'm a low security observer, I'm not allowed to see what the content of that exception is, but maybe I'm just allowed to see that there was some exception. So that's one possibility we're looking at. Another is combining non-determinism effects, with probabilistic languages, probabilistic variables, and then you can see that you want to interact the level of non-determinism with the probabilities on your variables. And there's been a few things this week which have made me think, like, oh, maybe we could do that in our calculus. So I'll be following up with people later. Now, I mentioned sequence earlier, so just to wrap up, this is an example of a distributive law between two monads. Now imagine if we graded it and said, well, we have a list of length n, and inside we have some effects which we annotated with E, so there's some sort of action E happening. And what sequence does is it repeats those effects n times. So with a graded distributive law, we can explain what's going on here. We can say that our length of list n is taking we've got e to the power of n because we've got e times e times e times e forever, however long the list is. So the grading gives us a way to understand a bit more of what's going on with effects inside of our function. And we can say, is this what I wanted? In this case, it is. And then we can use that to do more fine-grained reasoning. So if you're not particularly interested in coeffects, but you do things with effects anyway, then actually this notion could be very powerful for you. Thank you.
Thank you, Dominic. So questions? James.
James McKenna, LFCS Edinburgh. You said that the effects were structured by an pre-ordered monoid and the coeffects by a pre-ordered semi-ring.
Yes.
You said nothing about ordered structure. Can you speak to that, please?
Yes. So the ordering provides you a way to do over-approximation of effects and under-approximation of coeffects on the left. So that comes via the sub-rule. And in the paper, we explain how all of that interacts with the rest of the structure, and with the different kinds of distributive law, then that sometimes flips around the order and things. But yeah.
Other questions? There's one at the back, Neil.
Hi, Neil.
Hi, Neil Krishnaswamy, University of Cambridge. So whenever I see calculi with monads and comonads these days, I wonder what happens when you decompose the monad and comonad into the adjoint pair. Have you tried that?
We did try things like that in the beginning, and actually Shinya has a paper at FOSAX or ESOP this year, which shows you how you can decompose a graded monad into an adjunction, which is actually not that trivial. It's not as easy as the usual monad decomposition. You have to find still the limits of the Kleisy and the Eilenberg-Moore. And we have thought about trying to do this decomposition so that we could bring out a graded monad and a graded comonad from the same adjunction and see what that interaction is. But we found that really difficult, and we didn't make really any progress until, now that Shinya's done this work, maybe we could think about that again. Good question.
More questions? Yeah.
Who's speaking now?
Where are you, person who's
Stand
here.
stand up.
Hi.
Stand up.
Right. Manuel Behrens from Bamberg. So monads and having monad transformers is already quite complicated, and there are ways around that, like algebraic effects. Does that exist for comonads? Like, do you have algebraic coeffects, and can you mix them with algebraic effects to make all this distributivity stuff easy?
This is a very good question. So one of the things with graded monads is that the graded information can be quite fine-grained. So it could be natural numbers tracking costs, which is not something you can really do with algebraic effect handlers, because there you have an effect system which tracks what operations you're doing, but not some other kind of fine-grained notions that are really just to do with some other kind of analysis of the system. Oh, that's not true. Oh, fantastic. Okay. Huh? Okay, so that's not true. So I take that back. I don't know. So I don't think there's been any work about coeffect handlers specifically. There are certain notions of coeffect which overlap with effects, mainly when you just depend on something like the reader monad is also the product comonad. So if you're just depending on sort of reading one thing that's read-only, then that can be structured in both ways. And that might give at least one route into thinking about what a coeffect handler or coeffect cohandler would be. But I don't know of anything yet.
One last question.
Phil.
Phil, down the front here. Down the front.
Phil Wadler, LFCS, University of Edinburgh. You mentioned ring structure. So that comes up with provenance as well. I wondered if there might be a link there.
Yes, yeah. So I haven't done any work on that yet, but coeffects are fundamentally about tracking data flow via variables, and then we can connect that with effects, which is when you data flow out of a computation. So I think there's enough structure there to do something like that. I mean, it's already got this information flow flavor, so I think that'd be a really interesting line of work to look into. But we haven't done anything on that yet.
So just as a final comment, I thought that was a very clear explanation of things that could be quite unclear because it's fairly sophisticated. So I thought that should be graded A.
Thank you, Phil. Thank you.
Okay, we should stop there. So let's thank the speaker again.